Part E. What would the optimal capacity be if the demand equation for market 2 changed? What if we changed our pricing for market 2? We could potentially drive the demand up for market 2, couldn't we? Of course, we would still want to do this such that our profit is at a maximum. So what we're going to do is we're going to set up a new profit equation. We're not looking to have the maximum demand. We're looking to have the maximum profit still. So we're going to change our equations up a little bit. So taking my setup from the last question, what's going to change here is my P2 portion. So this part here is going to change. This is now going to be, and I'll do this in blue, it's going to be 120 Q2 minus 0.35 Q2 squared. So my revenue changes, thus my values here will also change. Anything with Q2 in it ends up changing. I have 120 minus 2 Q2, giving me 118 Q2. And then I have minus 0.35 Q2 squared. Anybody have trouble following those changes? We shifted our revenue. The costs are still the same. Okay, now trying to optimize this function, I'm going to set up my Lagrange equation. So I've got my Lagrange equation. It's a function of Q1, Q2, kappa, because this is a capacity problem, lambda 1, and lambda 2. It's going to be equal to my profit equation. And then I add on lambda 1 times my constraint 1, which is still going to be the same. It's going to be kappa minus Q1 plus lambda 2 times, still going to be the same, kappa minus Q2. The constraints don't change. It's only the profit equation that's changed. Now doing my derivatives, stealing from the previous page. The only derivative that changes is the one for Q2, because that's the only thing that has changing. So what we have here now is 118 minus 0.7 Q2 minus lambda 2. Okay, I did a lot of shortcuts there. Did anybody have any difficulty following those? Let me know and I can give you a summary of what I did. Okay. So those are my derivatives now. Now, if lambda 2 is equal to 0, meaning market 2 is non-binding, then these terms are going to be 0. My lambda 2's will be 0, and the derivative with respect to lambda 2 would also be non-existent. So then setting these equations to be equal to 0, I would have 0 is equal to 158 minus Q1 minus lambda 1. 0 is equal to 118 minus 0.7 Q2. 0 is equal to lambda 1 minus 10. And 0 is equal to kappa minus Q1. So now I would still know that lambda 1 is equal to 10. From the second equation, I've got 0.7 Q2 is equal to 118. That would give me a Q2 value of 168.6. I would substitute this lambda 1 into the first equation. I would get 158 minus Q1 minus lambda 1 would be 10. That would give me 148 minus Q1 is equal to 0. Q1 would be equal to 148. Subbing that into our last equation, I'd have 0 is equal to kappa minus Q1. 0 is equal to kappa minus 148. Kappa is equal to 148. I did that rather quickly because the only thing that changed was what my Q2 was. All the other calculations were the same as what we did in the last part of the question. So that's why I ran through them rather fast. This part here is the only part that ended up changing. So now let's check our constraint. Is our Q2 less than or equal to our capacity? So now I have a demand of 168.6. So is 168.6 less than or equal to 148? No. We priced it now so that we could be more profitable if we had a different capacity. So what we're going to do now is we're going to move on to assuming that market 2 governs. Market 2 is binding, I should say, and that market 1 is non-binding. Questions so far? Okay. So now, grabbing my derivatives, I have constraint 1 is non-binding now, so lambda 1 is equal to 0. So all of those do not apply. So now solving my system of equations. Where would you suggest I begin? How about the first equation? Oh, sorry, these all need to be set to be 0. Silly me. All of these are going to be set to be equal to 0. So now solving for the first equation, I get Q1 is equal to 158. Just moving the Q1 over to the other side. For the third equation, I just need to move 10 over to the other side. I get lambda 2 is equal to 10. I can then sub this into our second equation, and I get 118 minus 0.7 Q2 minus 10 is equal to 0. 108 minus 0.7 Q2 is equal to 0. Moving this over to the other side of the equation, I get 108 is equal to 0.7 Q2. Dividing both sides by 0.7, I get Q2 is equal to, I know the suspense is killing you right now, 154.29. So then I sub that into my last equation. 0 will be equal to my kappa capacity minus Q2 of 154.29. Therefore, my capacity is equal to 154.29. So, am I done? Are we done this problem now? We got a new capacity. Aw, man, you're right, Ray. I still have to check the constraint. So I assumed that constraint 1 is non-binding. I have to check constraint 1. So checking constraint 1, and that constraint was that Q1 would be less than or equal to kappa. I have my Q1 value of 158. Is that less than or equal to 154.29? Sadly, no. So this does not work. What do we have to do now? What this means now is that both constraints are binding. But I have a 3-variable problem. 2 constraints aren't going to solve my problem. I have 3 variables. Setting my 2 constraints to be equal to each other is not going to solve this problem. So I'm going to have to use all of the equations. So I'm going to go back to all of these equations. Do you guys, does anybody need clarity on what I mean when I say we have 3 variables and only 2 constraints, so it doesn't solve? Does anybody want clarity on that? Okay. So here, my constraints were kappa would be greater than or equal to Q1, and kappa would be greater than or equal to Q2. Those are my constraints. So when I'm trying to solve for these, I would change these to be equal to, and then I would try to solve for this system of equations. So I would go try to solve for this, and what I would get is my kappas would be equal to my kappas, and therefore I would get Q1 is equal to Q2. I can't get a better solution than that. There's 3 variables. The rules of systems of equations is if you have 2 unknowns, you need 2 equations as a minimum to solve for them. If you have 3 unknowns, then you need 3 equations to be able to solve for 3 unknowns, and so forth. For n unknowns, you need n equations to be able to solve for the system of equations. So here I had 1, 2, 3 unknowns, kappa, Q1, and Q2. The 2 constraints are insufficient. There's 2 equations here. They're insufficient to be able to solve for this system of equations. Does that answer, does that clarify that? Jared, Hunter? Okay. So, can't solve this using the constraints alone, but both constraints are binding. So how do we go about doing this? So what I'm going to do is I'm going to take all 5 equations. So I have 5 equations. All of these derivatives are going to be set to be equal to 0. This way, both constraint 1 and constraint 2 are being considered. I did not set either lambda 1 nor lambda 2 to be equal to 0. So now how many variables do I have? I've got Q1, Q2, kappa, lambda 1, and lambda 2. 5 variables, 5 equations. I can solve this using all of the equations. I can solve this system of equations while keeping both constraints in the equations, so both are being considered. So now it's tedious algebra time. Okay, so solving the system of equations. Let's start here. Let's take my lambda 1 over here. Tedious algebra means I should reference my notes. Okay, so this is going to become isolating my lambda 1, moving that over to the other side. I get lambda 1 is equal to, let me just move this over, 158 minus Q1. Lambda 2 I'm going to isolate, and I get 118 minus 0.7 Q2. Now I'm going to take both of these equations and I'm going to substitute them into the third equation. So therefore, I have 158 minus Q1 plus, now lambda 2, 118 minus 0.7 Q2 minus 10 is all equal to 0. This gives me, hang on, we have a question in the chat. Alex, I'll get back to that question after we're done solving this. Make sure that we understand that process. Okay. So now, working this through, I get 158 plus 118 minus 10 gives me 266 minus minus Q1 minus 0.7 Q2 is equal to 0. Now, I'm just going to leave that as is for now because I've got these two easier equations to work with as well. From this one, I can get kappa is equal to Q1. And from this equation, I can get kappa is equal to Q2. So I'm going to sub those into what I just did here as well. So now I have 266 minus kappa minus 0.7 times kappa, because Q1 and Q2 are both kappa, will be equal to 0. 266 minus 1.7 kappa will be equal to 0. 266 is equal to 1.7 kappa. Kappa will be equal to 156.47. So rounding that, because we can't have a portion of a seat, I'm going to set my capacity to be equal to 156 seats. So that's how we would handle when we have both constraints binding, but three unknowns. Okay, now to address your question, Alex. In the last question, question 3, we had both constraints binding, and we looked to solve where those two constraints intersect. So we have our two constraints, and ultimately what we're looking at is where they intersect. Now we could draw this y versus x, and ultimately what we're doing is looking for where those two lines intersect. So that would be 50 for the first constraint is equal to x plus y, and 60 would be equal to 2x plus y. What I solve for this system of equations, y would be equal to 50 minus x for the first equation. Subbing that into the second equation, I get 60 is equal to 2x plus 50 minus x. 10 becomes x. And then y becomes 40. That's what we did. We could solve for those values. Now let's go to what we just did. And I'm going to try to present this in a slightly different way than what I did earlier. Now what we're looking at is a 3-variable problem. We have capacity, Q1, and Q2. We only have 2 equations for our constraints. Capacity would be equal to Q1. Capacity would be equal to Q2. This system of equations is not able to be solved when we're looking at it this way. Basically, what this is saying, capacity is equal to Q1. On the Q1 capacity plane, we have something looking like this. On the Q2 capacity plane, we have something like this. We can't find a place where these intersect, can we? We're dealing with too many variables. So we cannot solve this system of equations because we have 3 unknowns and 2 equations. That means that this is unsolvable. The guiding principle to solving system of equations is that you need to have as many equations as you have unknowns. So when we have 2 unknowns, we need 2 equations, 3 equations, 3 unknowns, or basically it keeps going like that. So to solve this problem, we couldn't use that approach and we had to find a different approach. So we did have 5 equations. We have 5 unknowns within those equations. We can solve for that. Next question I see for Emma is, why don't we round the capacity up instead of down? So this is for profit. This isn't break even or something like that. This is for profit. So maximum profit is tied to this number, 156.47. So we're going to round in the natural sense to optimize our profit. What it means is that profit is going to be like this. At 156.47. So I'm going to choose the value that is closest to that between 156 and 157. And 156 is closer to 156.47, so I round to 156 for profit, because I want the highest profit. So if it was something like 156.77, I would go up to 157. You do natural rounding. Great questions. I'm over time. Oh my goodness, I'm over time by a lot. I'm sorry, guys. You guys are all excused. Sorry about that. I got caught up in your questions. Take care. I'll post those solutions and the new content shortly.